All right, let's see if we can sum up Chapter 4. Chapter 4 is almost entirely stoichiometry and types of reactions. So if we're going to do stoichiometry, what we're trying to figure out is how to go from some amount of starting material to some amount of what we need. And the way to do this is to start and balance your equation. Once you've got a nice balanced equation or balanced reaction, you need to figure out the moles of what you have, what your starting material is. If you have grams, you know you're going to divide by molar mass to get moles. We're going to use the coefficients in the balanced equation to get moles of what we need. So if we have A and we want B, we're going to use its mole ratio to go back and forth. Now, once we've got what we need or what we're looking for, we're going to take our moles of what we're looking for and get our answer to finish our question. If it's grams, we're going to again use molar mass to figure out how many grams it is of what we need. So let's do one. What mass of CO2 will be produced from the reaction of 180 grams of glucose with 180 grams of oxygen? So let's balance this sucker. C6H12O6. Well, we know that we're going to make 6 carbons, so that's going to be 6 carbon dioxides. We have 12 hydrogens, and they're coming in packages of 2 in the water, so 12 over 2 is 6 H2Os. So we have glucose, C6H12O6, plus some oxygens. Now, on this side, if we add this up, we're going to have a total of 18 oxygens. Here we have 6 already, so the rest are going to be over here in the O2. 18 minus 6 is going to be 12. 12 divided by 2 is going to give us a total of 6 oxygens. So, balanced equations. Now, once we've got balanced, we're going to have to figure out moles of our starting material, moles of what we have. Well, we have 2 different things. We have glucose and we have oxygen, so we're going to have to do both. 180 grams of glucose. To go from grams into moles, moles of what we have, again, we know is the second step. It's going to be 1 mole over the molar mass, which is 180 grams per mole, giving us a total of 1 mole of glucose. We're going to use the ratio in our balanced equation to get moles of what we need. Well, we need CO2, so 6 moles of CO2 for every 6 moles of glucose is going to give us 6 moles of CO2. We need grams because that's what we're being asked here at the end. So we know that's going to be multiplied by molar mass. So if we multiply this by 44 grams per mole, we're going to end up with a total of 264 grams of CO2, starting with our glucose. Let's do the same for oxygen. 180 grams of oxygen. We know to go from grams to moles, and again, it's always moles of what we have. We're going to divide by the molar mass. The molar mass of oxygen is 32. And that's going to give us a total here of 5.624 mole of CO2, mole of O2. We're going to have to get CO2, 6 moles of CO2 from our balanced equation for every 6 moles of O2. And again, remember, balance, moles of what you have, moles of what you need, what it is you're solving for, and that's going to require your balancing right here. And that's going to give us 5.624 mole of CO2. And if we multiply that by 44, we're going to get a total here of 248 grams of CO2. Now, we can't make both 264 and 248. We know that we are going to run out of something. And we know what we're going to run out of by looking at the smaller amount of the product, because as soon as we make 248 grams of CO2, our oxygen is gone. So oxygen is limiting. We will only make 242 grams of CO2. This would be a miracle, and there's no miracles in chemistry. All right, so theoretical yield and actual yield. Theoretical yield is just a fancy term for the amount of product that you would make, period. You don't even have to have a limiting reagent on this one. If you want to take and figure out how many grams of product you would make, you're calculating the theoretical yield. Now, if you have 2 reactants that you know about, and you're trying to figure out how much product, the one that comes from the limiting reagent is going to be your theoretical yield. So in this case, because we had 2 different amounts of products, we had 264 grams of CO2, or we had 248 grams of CO2. We know we can't make both. We make the least, and that is going to be our theoretical yield. The actual yield is the amount of product you obtain from the reaction in the lab. This is a lab amount, and you can only get it by going to the lab and doing this, or going to the lab and knowing what your percent yield is. Our percent yield, by definition, is actual over theoretical times 100. So let's calculate a percent yield. So if in this reaction we only make 235 grams of CO2, what is the percent yield? Well, it would be 235 grams actual divided by the theoretical, 248 grams. Again, remember that's the smaller amount, multiplied by 100, giving us a total of 94.8% yield. All right, let's try a different type of reaction. Let's say that instead now we are looking at precipitation reactions and we're trying to write balanced equations. For a precipitation reaction, what we're going to have here is we're going to make a precipitate, and we're going to find out our precipitate from the solubility rules. Now remember, these are given, and these are going to be on the equation sheet that you get with your exam. So if you're not sure what these are, go to the exam tabs and look at your equation sheet and realize that we give you the solubility rules. We're going to have to write our balanced equation. We're going to determine the precipitate from the solubility rules. We're going to write the ionic equation. And in this case, when we write our ionic equation, and don't lose the fact that that's ions, everything that is a strong electrolyte, totally ionized in water, will be a free ion by itself with its charge. If it's a solid, liquid, or gas, or a weak acid or base, they will be kept in molecular form. So, for example, we would never take water and break it apart, or carbon dioxide and break it apart, or HCN. And I don't expect you to know these right now, all the weak acids or bases, but HCN is a weak acid, and we would leave it in its molecular form. We're going to look at both sides of the ionic equation, and we're going to cancel out our spectator ions, and when we're finished doing that, we are going to have the net ionic. So let's do one. So if we have sodium carbonate with iron 3 nitrate, and a really good thing to do when you look at these is to make sure you understand the charges. Sodium is Na plus, carbonate is CO3 2 minus, iron 3 is Fe3 plus, and nitrate is NO3 minus. Now if we know what those are, the rest of this is fairly straightforward. So we're going to take sodium carbonate, which has to be Na2CO3, given to be aqueous, so we start out with AQ. We're going to react it with iron 3 nitrate, which is the FeNO3, and we're told that's aqueous as well. We also know that from the solubility rules. When we write the molecular equation, we are writing everything attached as if it were a molecule, even though we know it really isn't in real life. We're going to swap what's attached to what, which means we're going to put the carbonate with the iron, and we're going to put the sodium with the nitrate. When we do this and we look at the charges, we're going to have Fe2CO3, 3, and both sodium and nitrate are plus our charge of 1, so it's going to be NaNO3. Make sure you always write the cation first. Looking at the solubility rules, we know all group 1 compounds are soluble, so sodium is always going to be soluble, so we put an aqueous there. We know that carbonates tend to be insoluble, so this is going to be a solid for an S. Now we balance it. We start here. It's the most complicated molecule. 2 irons, 3 carbonates, 3 carbonates. When we look at this now, we're going to have 6 sodiums and 6 nitrates. So that's going to give us a 6 right there. And that is the molecular equation. Now, we're going to write the total ionic. The total ionic means we take anything that's aqueous and a strong electrolyte and break it into its ions. So if we do this, we're going to get 6 Na plus aqueous plus 3 CO3 2 minus aqueous, and do not forget the charges, plus 2 Fe3 plus aqueous, plus 6 NO3 minus aqueous. It's going to make our products. The solid we're going to leave as a solid. We know this is a precipitate. We know that this is not going to be a strong electrolyte. It's just going to be a solid in the bottom, so we leave it just like that. And we go back to our sodiums. 6 Na plus aqueous plus 6 NO3 minus aqueous. So now we take and cross off our spectator ions. Sodium and nitrate are in the same form on both sides. They're not involved in the reaction. They are unchanging, and they are spectators, leaving us with 3 carbonate plus 2 irons makes an iron 3 carbonate. And that is going to be our molecular equation, our total or complete ionic, and this is going to be our net ionic with the spectators removed. All right, how about acid-base? Acid-base neutralization reactions are what happens when an acid and base neutralize each other's properties. You're going to make salt and you're going to make water. If the salt is soluble, meaning it's going to be a strong electrolyte, your net ionic is H plus OH minus, it goes H into H2O. So as long as we make an acid plus a base giving us a salt and water, we're going to have an acid-base neutralization reaction. So let's do some math with one. What volume of sulfuric acid is required to neutralize this amount of KOH? Well, we know that our steps are this. 1, balance. 2, moles of what you have. 3, moles of what you need. 4, finish. Okay, now we can't do the dilution equation on this because this isn't a dilution, this is a reaction. This is not one-to-one. So we are going to have to take and write a nice balanced equation. So our balanced equation is this: H2SO4, aqueous, is going to react with KOH. When we do these reactions, it's very important to realize that what we're really getting is an H plus an OH minus. Again, the cation from the acid with the anion from the base, making HOH or H2O. Everything else is probably going to be a spectator ion. So if I look at this, I have 2 H's, I need 2 OH minuses, and I'm going to make 2 H2Os. For every H plus we bring in, we need an OH minus to react it with, and our other species is K2SO4. Now, when we're taking and doing stoichiometry, we do not need our net ionic. We only need the molecular equation because that gives us our ratios. So, 1, we've balanced. 2 moles of what we have. Well, we have potassium hydroxide. We know that volume in liters multiplied by molarity is equal to moles. So if we take 0.040 liters of 0.40 molar KOH, we're going to get moles of KOH, which is 0.016 mole of KOH. We know our next step is moles of what we need. Well, moles of what we need is sulfuric acid. We know our ratio is 2 to 1, so we have 1 mole of H2SO4 for every 2 moles of KOH from our nice balanced equation. And again, we know we go from here to here with our balanced equation. That's going to give us 0.008 mole of H2SO4. And then we have to finish it. Well, when we finish our problem, we're going to go back to what we're looking for, which is volume. Well, we know that volume in liters multiplied by molarity is equal to moles. So we're going to have 0.008 mole. We're going to divide by the molarity, which is 0.25 mole per liter. And that's going to give us a volume of 0.032 liters or 32 milliliters. All right, with that in mind, let's do the last thing, which is redox. So in the following reaction, what is being oxidized and what is being reduced? We know that oxidation is loss of electrons. And if we're going to have loss of electrons, we're going to look at it and we're going to realize something is going to become more positive. Now, reduction is gain of electrons. If something is going to gain electrons, it's going to become less positive. So with that thought in mind and realizing that nitrate is a spectator, we have Fe2 plus reacting with Al is going to go into Al3 plus Fe. And when we determine what is being oxidized and what is being reduced, we are going to start always at the reactants. So we're going to have to see what is becoming more positive and what is becoming less positive. Well, if we look at aluminum, it is becoming more positive, which means it's going to be losing electrons, which means that aluminum is being oxidized. Iron is becoming less positive, which means it's gaining electrons. So iron is being reduced. And the key here is to make sure that you're paying attention to what's happening as we go from the reactants to the products, and then you're going to have it with that.